Today we're going to look at Chapter 2, Part A, over basic chemistry. We'll be looking at biochemistry as well in Part B. The reason we're doing a chemistry review is just because the body is made up of chemicals, and chemistry underlies all physiological reactions, which allow us to move, digest, allow the heart to work, even the nervous system to work. So let's start with something simple, matter. And matter is just anything that occupies space and has mass. So anything that's made up of stuff and takes up a particular volume of area. The three states of matter are solids, liquids, and gases. And solids have a definite shape and volume, so bones and teeth are a great example in the human body. Whereas liquids have a definite volume but changeable shape. Liquids will take on the shape of their container. An example in the human body would be blood plasma. And then gases have a changeable shape and volume, and the air we breathe would be an example. The air we breathe, for example, is going to be condensed as we inhale it in order to fit into the bronchial tubes and spaces to get to the air sacs or alveoli of our lungs. So there is a changeable shape and volume to gases. We'll also just briefly talk about energy. And energy is the capacity to do work or put matter into motion. There's different types of energy. For example, kinetic energy is energy in action. You can't actually see energy, but you can see what energy does. You can see the effects on matter that energy has. And if you see, for example, someone ride a bike or throw a ball or even push a swinging door and set it into motion, that's an example of kinetic energy. But all things that can move do have stored energy or inactive energy as well. That is potential energy, the ability to do work. The skeletal muscle in your legs has the potential to contract and allow you to stand up. Just as if someone was going to throw a ball but hasn't yet, they have the possibility to do that. Therefore, there's stored inactive energy in the skeletal muscle of their arm, and that will get turned into kinetic energy when they do throw the ball. Kinetic energy can also be transformed into potential energy and vice versa, just as when you're riding a roller coaster. The potential energy that you build as you go up the first hill turns into kinetic energy as you go down the hill or crest the hill. There's also different forms of energy: chemical, electrical, mechanical, and radiant. Radiant energy is going to travel in waves, whereas mechanical energy is going to be a little bit more direct and involved in moving matter, such as when you push the pedals of a bike in order to move it forward. There's also ions that participate in electrical energy in order to allow things like the nervous system to use electrical currents and communicate cell to cell. And there's even chemical energy such as ATP, which is adenosine triphosphate. That's an energy molecule that stores energy in its terminal third phosphate, and it can release that energy if you break off the phosphate. Now let's start to focus on the composition of matter. And all matter simply is just composed of elements. The periodic table is a complete list of the 118 recognized elements, and we can't really break down elements into something simpler, something slightly different by ordinary chemical methods, but we do know that atoms make up elements. Elements are actually composed of only one type of atom. But since they're composed of only one type of atom, that means that all the atoms that make up an element have similar physical and chemical properties. And we'll talk more about atoms and elements as we go forward. Let's also compare elements to molecules. Hydrogen is an element. Oxygen is an element. But water, which is represented by the chemical formula H2O, is a molecule. Molecules are still types of matter that cannot be separated into others, but they can be separated into other elements, but still not by just ordinary separation means, not by evaporation or anything like that, because molecules involve chemical bonding. So water is always water unless we actually break bonds. But if we do break bonds, we would be left with essentially the elements that make up molecules. So if you think back to Unit 1 or Chapter 1, you can think back to the fact that atoms, which make up elements, can combine to form molecules, and then molecules can combine to form even bigger structures like organelles. And then if you think of that structural organization system, we eventually got up all the way to the organism. So for Chapter 2, we're really just focusing on the small stuff. We're not going all the way up that hierarchy of organization. So let's talk more about atoms. Atoms are the building blocks for elements. Elements are made up of just one type of atom, and oftentimes you can use element and atom interchangeably because atoms define what an element is, because what an atom has as its chemical and physical properties is what the element has as its chemical and physical properties. So they're essentially the same thing except in size. There's a lot of atoms that make up one element, but they're all the same type. Here we have two squares from the periodic table, and we're just looking at things you could find on the periodic table, like the atomic symbol or chemical symbol, which is a 1 or 2 letter chemical shorthand for each element, like C for carbon or K for potassium. Other things we're going to talk about you can find on the periodic table are the atomic numbers and atomic mass. Atomic number is just the number of protons. Mass number is going to be equal to protons plus neutrons. Those are subatomic particles located in the nucleus of an atom, and we're going to talk more about them. And then atomic weight is just the average of mass numbers of all isotope forms of an atom, and we're going to learn what isotopes are. So this is a quick guide that I recommend you come back to once we've gone through the rest of this PowerPoint, because this, again, is a quick guide, so not all the information is being provided to you here. So let's move forward. Here's the periodic table of elements. And in questions about either the periodic table or about atoms or specific elements, you'll be given information like atomic number or number of neutrons or number of electrons or protons. So you'll be given all the information that you need in order to figure out the answer to your problem. But periodic tables in general oftentimes have a key that tell you what the information they provide are. We have a color key over here, but we're more interested in this key where we can see where the atomic mass is located in this periodic table, where the atomic number is located, and even the chemical symbol and the written out elemental name. Forward. Alright, let's talk now mainly about atomic structure. So we'll kind of start from the beginning, break everything down in more detail, and build up eventually to molecules and compounds. So if we talk about atomic structure, we have to talk about the fact that atoms are made up of really small particles. These particles are called subatomic particles. There's 3 subatomic particles that differ in how much they weigh, their charge, and where they are in the atom. The 3 subatomic particles are protons, neutrons, and electrons. Now, protons are positive in charge. Neutrons are neutral in charge, and electrons are negative in charge. So those are definitely pieces of information you want to know about the 3 subatomic particles. So let me give you 2 separate lists now. If you were asked to list the 3 subatomic particles, you would say protons, neutrons, and electrons. Those are the 3 subatomic particles that you find in individual atoms. If you were asked to list the charge of the subatomic particles, you would say protons are positive, neutrons are neutral, and electrons are negative. And this is always. Protons don't suddenly become negative, and electrons don't suddenly become positive. Now we also want to know the location of these subatomic particles. And 2 of them are located in the nucleus, or the central region of an atom, and 1 is located around the nucleus in what's called an orbital. So protons and neutrons are located in the nucleus, or the central region of the atom, whereas electrons are located in the orbital. It is important for you to know the name of the subatomic particles, their charge, and their location in an atom. The only other information on this slide is the AMUs, or arbitrary measurement known as atomic mass unit, that is given for each subatomic particle. And the reason I'm calling it an arbitrary measurement is not because it's not useful. It's just only really useful for atoms, so it's not going to transfer into kind of other processes or other chemical structures. So the reason that we have AMUs is a quick and easy way to compare how much protons and neutrons weigh to electrons. And essentially all it means is that electrons hardly weigh anything. They're really, really small. So we said that they had a weight of 0 AMUs, and compared to electrons, neutrons and protons, even though they're small, weigh more. So we gave them an AMU weight of 1. So it's arbitrary because all it means is protons and neutrons weigh more than electrons. It just doesn't mean a whole lot outside of atomic structure. So here is figure 2.2, just showing you the atomic structure of 3 of the smallest atoms. We can see that the red protons and the yellow neutrons are in the central region of each atom. So that area is called the nucleus. And then we're looking at the planetary model of atoms. It's really easy to study atoms with the planetary model versus what we'll look at later called the electron cloud model. And so oftentimes when you're looking at atoms or learning about them for the first time, we'll see this planetary model that has orbits. We can see hydrogen has 1 orbital, just like helium, and then lithium has 2 orbitals. And there's gray electrons in the orbitals. Since hydrogen only has 1 electron, it only needs 1 orbital, and there's one electron in its orbital. There's 2 electrons in helium's orbital. It only has 2 electrons. And then for lithium, it has 3 electrons. In the first orbital, there are 2 electrons. In the second, there's just 1. So we're out of electrons, but why did we stop at 2? Why did we need 2 orbitals? Why did we need another orbital for that 1 extra electron? And that is due to the octet rule, which again is coming up. We'll describe it in detail. But the octet rule says simply that the first orbital is happy with 2 electrons, and then all the orbitals after that would like 8. But that's why we moved from the first orbital to the second orbital when we had more than 2 electrons for an atom. Alright, but not just where are the subatomic particles. What are the subatomic particles doing in an atom? And what they're doing is giving it a neutral charge, because as long as your atom hasn't participated in bonding, as long as there's no information that's being given to you saying that they're not neutral, we can assume that all atoms in questions are electrically neutral, meaning that the number of positive charges is going to be equal to the number of negative charges. That means if you know the number of protons for an electrically neutral atom, you know the number of electrons. So unless you're given information that says your sodium atom, for example, has a positive 2 charge, or your lithium atom is a negative 1 charge, unless you're given information like that, which you will not be for this class, you can assume always that the number of protons equals the number of electrons, because neutrally uncharged atoms have to therefore be electrically neutral. So protons and neutrons we know found in the nucleus. Electrons we saw orbiting the nucleus. What we just looked at was a planetary model, and we're also going to see an orbital model as well. The planetary model is really simplified, it's outdated, but it's really helpful. That's why it's lasting. That's why we see it persist into new textbooks. But it is incorrect because it depicts electrons in orbits in fixed circular paths, and while it's useful for illustrations, that's not how electrons exist. Electrons actually exist in electron clouds. They exist in what we could call a pseudo-orbital. They definitely rotate or go around the nucleus, but it's a lot harder to dictate where they might be located than the planetary model suggests. So instead, there tends to be shading regions in the orbital models, which suggest greater electron density versus lesser electron density. So for predicting the chemical behavior of atoms, which we won't do a whole lot in this class, the orbital model would be more useful. So here you see the planetary model on the left, useful for learning and illustrations, and the orbital model with its electron cloud on the right. The electron cloud encompasses the location where you could possibly find electrons. Since they're rotating, it's assumed you could find them anywhere at any point in time. If we were to freeze an atom, we would just have to see where they landed. Next, we're going to be looking at how to identify elements. And the best way to learn how to identify elements is to use a periodic table and to look for the chemical symbol. But you can also look at the atomic number. The atomic number is really just equal to the number of protons, but the reason that it's useful for identifying elements is all atoms, all elements, have unique atomic numbers. For example, the atomic number of hydrogen is always 1. if the atomic number was 2 or 3 or 6 or 5, then we would not be looking at hydrogen. So the atomic number, which is the number of protons in an electrically neutral atom, is unique to that atom or element. Other identifying facts would be mass number, different isotopes, atomic weight. And we've already talked about mass number with the sum of protons and neutrons. But now you know what protons and neutrons are. They're subatomic particles. Now you know where they're located in an atom. They're located in the nucleus. And you also know that they arbitrarily weigh more than electrons. Both protons and neutrons weigh 1 AMU. So if each one weighs 1 AMU, or essentially has a unit of 1, you can just count how many of each you have in order to get mass. So you have 5 protons, 5 neutrons, you have 10 AMU. That's why the mass number is the sum of the number of protons plus the number of neutrons. And if you know, again, the number of neutrons and mass number, you can rearrange the equation to find number of protons. Or if you know the number of protons and mass number, you can rearrange the equation to find number of neutrons, as long as you know 2 of the 3 pieces of information. Here's just a quick example for finding atomic mass number with the math written out. So if you have 6 protons, 6 neutrons, in order to find the atomic mass, you just add those together, and the answer there would be 12. And if you've been wondering what an isotope is, we're finally going to talk about it. An isotope is a structural variation of an element. So it's otherwise the same, except isotopes of an element have different numbers of neutrons. Otherwise, they're exactly the same as the other variations. So for example, if an atom normally has 2 neutrons, and you see an atom that has 3 neutrons with the same number of protons as the original, they're isotopes of each other. So atomic numbers are the same, but mass numbers are different because of the different number of neutrons in isotopes. And isotopes come into play in order to calculate atomic weight, because atomic weight is the average of the relative weights or mass numbers of all the isotopes of an element, but we have to take into account the abundance of that isotope in nature. So let's look at some examples. So here we have isotopes of hydrogen. Now, the isotopes of hydrogen actually have different names, like deuterium and tritium. But hydrogen is the most abundant, or the more common, of our isotopes that we see here. But if you look at these isotopes, they're all slightly different. But if we look at what's different, it's only the number of neutrons. Hydrogen, deuterium, and tritium all only have 1 proton, which is important because the number of protons tells us what atom we're looking at. So these are all the same type of atom. They're just slightly different because they have different numbers of neutrons. So hydrogen has no neutrons, deuterium has 1, and tritium has 2. They also all have 1 electron, which makes sense because none of these atoms are charged. So we'd have to match up the number of protons with electrons so that our positive and negative charges cancel out. The only other difference we can see besides the number of neutrons is the atomic mass, which makes sense. Atomic mass is the number of protons plus neutrons. Well, if I only have 1 proton here, my atomic mass is close to 1. If I have a proton plus a neutron, my atomic mass is close to 2. And if I have 2 neutrons and 1 proton, my atomic mass is close to 3. So the differences you see among isotopes, which are variations of atoms, is the number of neutrons, which will affect the atomic mass. Now, the atomic weight of hydrogen that's reported on the periodic table is actually an average. And it has to be an average because we know by seeing what we see right here in this slide that hydrogen, deuterium, and tritium are all hydrogen atoms, or types of hydrogen atoms. So which atomic mass do we choose to put on the periodic table? We don't choose one, we just average them out. But we have to average them out based on how many exist in the world, or in the environment, or in nature, however you want to think of it. And most of the hydrogen atoms look like the one on the left. So the hydrogen over here with just one proton, one electron, no neutrons. So if we were adding up all of the numbers of hydrogen, and then some of the deuterium, some of the tritium, and then dividing by the number of atoms that we're taking into account, the average is going to look like the isotope variation that is in the most abundance. And in this case, it's hydrogen with an atomic mass of 1.008 AMU, and that's why the atomic weight that's reported on the periodic table looks like the atomic mass for that variation. It's actually an average, but since hydrogen is the most abundant, the average looks like that atomic mass. All right, and if you just got confused, here's another example. If everyone in the class failed a test, but one person passed with a 100. So everyone but this one person failed the test, but one person got a 100. And I was trying to give you guys the class average. Is the class average going to look like the 100 or the failing grades? It's going to look like the failing grades because they're in more abundance. So that's just what happened here. I have 3 different types of hydrogen. If I want to get the average, I have to take into account which one do I have more of. I have more of the hydrogen with 1 proton and no neutrons. So my average is going to look like its weight. So the grade in the other example is taking the place of the mass in this example. All right, let's look at something else. All right, so how about carbon? Carbon has isotopes. There's carbon-12, carbon-13, carbon-14, but they're not all going to be present in the same amount. So, for example, you have carbon-12 isotopes in this example present at 1.11%. Carbon-13 isotopes are going to be present. Oops, I'm reading that wrong. In this example, you have carbon-12 present at 98.89%, carbon-13 present in the environment at 1.11%, and then only a small amount or trace amounts of carbon-14. So they don't even give us a percent because there's so little. So we know that the mass of carbon-14 is not going to be what is reported to the periodic table. It's not going to look like carbon-14. There's so little of it. So if we had to guess what the average or atomic weight was that's reported to the periodic table for carbon based on these isotopes, we would guess it looks the most like carbon-12 because it's the most abundant in nature. So what it's saying is for each element in nature, there are some of those normal atoms with equal numbers of protons and neutrons, and there are some atoms with unequal numbers, and the amount of particular isotope, so with different numbers of neutrons, can be averaged in order to get a percent abundance or amount of that isotope in nature, and that's going to help us determine the atomic weight or mass, because the one that's more abundant is the one that we're going to kind of give more stock into when we're reporting a weight or atomic mass in the periodic table. This won't come into a lot of play in this class. You won't have to do a lot as far as calculations are concerned with atomic mass versus atomic weight. I just want you to be aware of where we're getting this term atomic weight, which is what's actually being reported as mass on the periodic table and is an average number. So in summary, for any element, if you know the number of protons, you know the atomic number, because atomic number is just number of protons. If you know the number of protons, then you know the number of electrons, because in this class, all of the atoms we look at when we're figuring out that information are going to be electrically neutral. When you look at mass number and you have number of neutrons, you can figure out the number of protons. Or if you have the number of protons and mass number, you can figure out the number of neutrons. So the equation mass equals number of protons plus the number of neutrons is going to be a useful equation. Here we actually see it rearranged to find number of neutrons. We could say number of neutrons is equal to mass number minus atomic number, and you could just put right here the number of protons, because again, same thing. So let's look at oxygen and actually look at the information that's given to us and how we can use it to figure out the other information. So if you were given that the atomic number of oxygen is 8, and then asked the number of protons, it's just 8, because the atomic number is same as number of protons. If you were given, again, oxygen has an atomic number of 8, which is going to stay the same always for oxygen, and you were asked to find the number of electrons, and this atom is neutral as far as you know, then the number of electrons is also 8. Because in an electrically neutral atom, the positive charges have to match up to the negative charges in order for the atom to be neutral. And then if you were asked to find the number of neutrons in this atom, you could use the equation mass number minus atomic number, which is just number of protons, to find the number of neutrons, which is also 8. Because the mass number you were given was 16. So if you're still confused about the difference between mass number and atomic weight that we just got done talking about, that thing that was the average of how abundant an isotope was in nature, please first go review what an isotope is, which are just variations of atoms with different numbers of neutrons, and then look at the mass number and atomic weight information. But you can also find plenty of videos on YouTube. Just email me if you want a suggestion. But let's test ourselves. Alright, first and foremost, all atoms of the same element have the same number of protons. How about the smallest unit of an element is a or an atom. Atoms are composed of which 3 subatomic particles? You said protons, neutrons, and electrons. You're correct. And each of 2 or more forms of the same element that contain equal number of protons but different numbers of electrons is called a or an isotope. Alright, next we're going to move on and look at molecules and compounds. Before you move on, make sure you're really comfortable with the terms that were discussed in that first part of the Part A PowerPoint for chemistry. Alright. Molecules and compounds. Most atoms aren't existing all by themselves in a free state all alone. Actually, they combine with other atoms. So a molecule is just a really general term. So anytime you have atoms, so 2 or more that are bonded together, we would call that a molecule. You could have the same types of atoms or different types of atoms bonded together, and it's still a molecule. Like oxygen gas, which is 2 oxygen molecules. That's a molecule. Or water, which is 2 hydrogen atoms and an oxygen atom, that's a molecule. So anytime you have 2 or more atoms, whether they're same or different, combined chemically, that's going to be a molecule. But you can only call something a compound if you have 2 or more different kinds of atoms bonded together. So for example, water is a compound, but oxygen gas is not. Carbon monoxide is a compound, but 2 hydrogen atoms together would not be. And table salt is a compound. But if you just had a bunch of carbon bound together, that would not be a compound. Another way to say this is that all compounds are molecules, but all molecules are not compounds. And I'll say that again. All compounds are molecules, but all molecules are not compounds. Because molecule is the general term, it's kind of the broader term. You say something's a molecule, it just means that you have atoms bonded together. Doesn't matter if they're the same, doesn't matter if they're different. A compound is more specific, and you can only use it if the 2 atoms bonded together are different. Let's also look at mixtures. Mixtures are going to be how most matter exists, and it's when 2 or more components are physically intermixed. A good example of a mixture just to always think about is sand and water. Water is H2O, sand is made up of carbon components and other atoms, but if you mix them together, 2 separate chemically bonded things mixed together, you've made a mixture. There's 3 types of mixtures: solutions, colloids, and suspensions. So a solution is when a solute particle is really tiny, it doesn't settle out or settle at the bottom if you were to mix it in with a large aqueous solution like water, and it doesn't scatter light. Light would shine right through it. So mineral water would be a great example. It's usually homogeneous or the same throughout. Anywhere in the bottle of mineral water, we should have about the same amount of minerals at the top as we do in the bottom. That would be a solution. Very well mixed as well. A colloid has slightly larger solute particles. They don't settle out, but you might be able to see them. A good example is Jello. You're not always able to see the solute particles in a colloid. For example, the Jello we can see was made by mixing sugar and other granules together with water in order to make a gel-like solution. A lot of the times colloids are going to be gel-like. An example of a colloid in the human body is the cytoplasm of cells, specifically the cytosol part, which is jelly-like and holds organelles. And then a suspension is going to be the only example of a mixture we look at where the solute particles actually do settle out. They're really large. If you leave a suspension over time, all of the components will separate out. You can also use instruments like for blood, which is also a suspension. You can use instruments like a centrifuge to speed up the settling out process. So this list, solution, colloid, suspension, is organized from smallest to largest solute particles dissolved in a solvent, which is the dissolving medium, and the only ones that settle out would be the ones or solutes in a suspension. So let's talk more about a solution. So again, solutions are homogeneous, so that means the particles or solutes are evenly distributed throughout the solvent. If you're wondering what the solvent is, it's going to be the substance that's usually present in the greatest amount. It's the substance that does the dissolving. A lot of times it's a liquid, like water. Solutes is pretty much what's going to be dissolved in the solvent. So solutes are the substance present in the smaller amount. It's what's dissolved in the solvent, and blood sugar would be an example, where glucose is a solute, and blood, especially the watery plasma, is the solvent. If something is a true solution, it's going to be transparent. So again, mineral water was a great example, but air is an example, a salt solution, sugar solution. Those are all good examples. Colloids and suspensions are going to be heterogeneous. They're also known as emulsions, but we're going to call them colloids in this class. What it means to be heterogeneous is that the particles are not evenly distributed throughout. Because Jello is a good example of a colloid, I like to use kind of an exaggerated version of the Jello example. Think of fruit Jello, and think of all the fruit getting accidentally deposited at the bottom of the fruit Jello. Well, if we were to take a sample at the top of the Jello mixture and at the bottom of the Jello mixture, they would be different, so they would not be the same. So it's a heterogeneous mixture because the amount of solute, the fruit, in the solvent, the Jello, would not be the same throughout. But we'd still see that the fruit doesn't settle out or completely try to separate from the Jello. It remains at least slightly mixed in. A lot of colloids associated with a sol-gel transformation, where you see a solution or a liquid turn into a gel. And again, a great example in cells is cytosol, or the jelly-type part of cytoplasm. Blood's a good example of a heterogeneous mixture called a suspension. It contains really large visible solutes that do settle out. The solutes that settle out in suspensions, in this case, our blood example, are actually cells. Blood's considered a suspension because if left in a tube, the blood cells will settle out all by their own, or on their own. But you can use a centrifuge in order to speed that up, which is a tool that just spins the blood sample around really fast to separate the components. So here's a good review sheet for compounds versus mixtures. So compounds are chemically pure. So for example, if you have water, which is H2O, it's always water. If you separate the hydrogen from the oxygen, it's no longer water. So as long as it maintains or remains a compound, it's chemically pure. All the molecules will be identical. It won't be really easy to separate or break the bond, so they can't be separated very easily by physical means. And since it's chemically pure and all the molecules are identical, it's homogeneous. Whereas mixtures are composed of two or more components, two or more different chemical components like sand and water. No chemical bonding needed. Doesn't actually occur in mixtures. Most mixtures can be separated by a really easy physical means. So if you take your sand and water example, just leave whatever container holds the sand and water out in the sun and the water will evaporate and you'll be left with the sand. Really easy physical means of evaporation to separate those two components. And mixtures can be homogeneous or heterogeneous, although we just saw that most mixtures are heterogeneous and only solutions are mixtures that are homogeneous. So the only mixture that is homogeneous is a solution. Let's do an example where we test if we really know what a solvent or solute is. So a solute is what gets dissolved, a solvent is what does the dissolving. So in the example, salt water, what is the solvent? You said water, you're correct, and that would make the solute salt. So if you said salt, you're correct as well. And here's another review slide for mixtures. Let's get that out of here. Here's another review slide for mixtures, specifically looking at colloids and suspensions. Colloids and suspensions are both the heterogeneous parts or types of mixtures. That means that they're not going to be the same throughout. And suspensions by far have the largest visible solutes and they settle out. And so what we just went over were the three main differences between compounds and mixtures. And so we looked at whether the components were chemically pure, whether or not there was chemical bonding. There was not in mixtures, there was in compounds. We saw that mixtures could be separated by physical means, compounds could not. And then we saw that mixtures can be heterogeneous or homogeneous, whereas compounds are only homogeneous. Next, we're going to be looking at different types of chemical bonds. So make sure to watch that part of the video as well.